LLM architectures. Encoder versus decoder versus hybrid. Add a triangular matrix with negative infinity values. Congratulations, you've just turned BERT into GPT. That sounds like an oversimplification. It's literally true. The entire world of large language model architectures, from text understanding models through code generators to machine translation systems, reduces to one technical decision: the shape of the mask in the attention mechanism. If you've been with us in episodes 4 and 5, you already know the QKV matrices and the softmax formula. In a moment, you'll see how adding one triangular matrix changes the entire philosophy of language processing. Specifically, after this episode, you'll understand why BERT reads everything at once, GPT writes word by word, and T5 bridges both words. You'll see 6 reasons for decoder dominance. You'll also learn why encoders haven't died at all. On the contrary, they are experiencing a quiet renaissance. Since the difference boils down to the mask shape, let's see exactly what an encoder sees when the mask doesn't exist. Encoder reads everything at once. In an encoder-only architecture, every token sees every other token in the sequence. No mask means full bidirectional visibility. The encoder's attention matrix is a square L by L table in which all elements are non-zero after softmax. Here's what this means in practice. Take the word bank. In the sentence, "the bank vault was locked," the encoder assigns it a different representation than in the sentence, "we visited the river bank." This happens because the encoder analyzes the entire context simultaneously. It sees everything, from the first to the last word. BERT's topology is precisely defined. Token embedding plus position embedding, followed by n layers repeating the same pattern. Bidirectional self-attention, add and norm, feed forward, add and norm. The special CLS token serves as the entire sentence vector for classification tasks. The training objective is masked language modeling. 15% of tokens are randomly masked, and the model guesses them based on context from both sides. The key limitation: only about 15% of tokens participate in the gradient at each step. This makes MLM less sample efficient than next token prediction, where 100% of tokens provide signal. The encoder structurally cannot generate text. No autoregressive mechanism, no causal mask, no generation loop. It sees everything at once, yet that's precisely why it can't decide what to say next. This isn't a limitation, it's the design consequence of full visibility. The analogy is straightforward. An encoder is a business analyst on a project team. They read all the documentation cover to cover, see the full context, and produce precise summaries and classifications. They don't write code. Production applications are impressive. Google Search has been using BERT since 2019. The company called it the biggest leap in search in 5 years, with impact on roughly 10% of English language queries. Classification, entity recognition, semantic search, embeddings for RAG systems. Everywhere you need to understand text, the encoder is indispensable. The encoder reads everything at once. But what happens when you need to write something new, word by word, without seeing the next sentence yet? Decoder writes word by word. The decoder adds an upper triangular matrix filled with negative infinity values to the attention scores. GPT-2 uses the value -1 billion. After applying softmax, those values become exactly 0. A lower triangular attention pattern emerges. Each row sums to 1, but attention is drawn exclusively to past tokens. One matrix, one addition, suddenly a model that saw everything sees only the past. This is the change I mentioned at the beginning. Add a triangular matrix with negative infinity, and BERT becomes GPT. The decoder's training objective is next token prediction. The model maximizes the probability of the next word given all previous ones. Loss is computed on 100% of tokens, a key sample efficiency advantage over MLM. Decoder-only blocks removed the cross-attention layer from the original transformer. Each block is masked self-attention, add and norm, feed-forward, add and norm, linear projection, softmax. Scaling is parametric. GPT-1 with 117 million parameters in 2018. GPT-3 with 175 billion in 2020. GPT-4 as a mixture of experts model in 2023. 4 orders of magnitude in 5 years. Without optimization, K and V vectors for all previous tokens are recomputed from scratch at each step. Quadratic cost. KV cache solves this problem. It stores K and V vectors from previous steps. At each new token, the model computes attention only for one new query using the stored history. Reduction from quadratic to linear cost. 2 inference phases of the decoder are critical for production cost optimization. Prefill. The entire prompt in one pass, parallel like an encoder. Decode, token by token, sequential. That's the actual cost bottleneck. The decoder is a developer on the project team. They write code line by line. Each next line builds on the previous ones. They can't see the lines they haven't written yet. This asymmetry between reading and writing, between understanding and generation, is fundamental. The encoder reads, the decoder writes. But what if a model needs both capabilities at once? Encoder-decoder. Bridge between worlds. The original transformer from 2017 is precisely this encoder-decoder architecture. 6 encoder layers plus 6 decoder layers connected by the cross-attention mechanism. In one architecture, 3 types of attention cooperate. First, encoder self-attention, bidirectional, no mask, exactly like BERT. Second, decoder masked self-attention, causal, with a triangular mask, exactly like GPT. Third, cross-attention. This is the key to the entire architecture. In cross-attention, the query comes from the decoder, while key and value come from the encoder's output. The attention matrix is rectangular, L target by L source, because the input and output sequences can have different lengths. This is a fundamental difference from the square matrices of self-attention. Here's how it works in practice. The encoder processes the entire input once, creating rich contextual representations. These representations become K and V in every cross-attention layer of the decoder. At each decoding step, the decoder generates Q from its current state and queries the encoder for the most relevant portions of the input. Imagine translating the sentence Le chat noir into the black cat. The decoder generating the word cat focuses attention on chat in the encoder's matrix. Then, generating black, it shifts attention to noir. Cross-attention dynamically points to which portions of the input are most relevant right now. The encoder runs once on the input. Its output is reused in every decoder layer and at every generation step. This is an elegant architectural pattern. The encoder-decoder is a tech lead on the project team. First, they read and understand the specification. That's the encoder. Then they drive the implementation. That's the decoder. Cross-attention is the moment when the developer reaches into the analyst's documentation for a critical piece of information. T5 Unified NLP. Every task formulated as text generation. Translation, translate English to German, input, and the model generates output. Classification, call a sentence, input, the model responds acceptable or not acceptable. The encoder-decoder architecture proved harder to scale than a pure decoder. 3 architectures, 1 mechanism, 3 masks. So why did one of them, decoder only, dominate the entire world of AI? 6 reasons for decoder dominance, decoder-only dominated AI. Not because it's better, but because 6 converging factors created an unbalanced advantage. First, simplicity of scaling. 1 block, 1 training objective, no specialized heads for specific tasks. Second, sample efficiency. 100% of tokens in the loss function versus 15% in MLM. Yitei, senior research scientist at Google Brain, put it directly. In denoising-based training objectives, only a small fraction of tokens is masked. This translates to low sample efficiency per flop. Third, unified interface. Every task is text generation. No need to design separate classification heads. Fourth, in-context learning. GPT-3 demonstrated that decoders can learn from examples in the prompt without gradient updates. One model handles thousands of applications. Fifth, KV cache. Causal attention enables efficient caching of K and V vectors. Sixth, infrastructure momentum. CUDA kernels, flash attention, VLLM, the entire ecosystem optimized for autoregressive generation with causal masking. An important nuance from Yitei. Bidirectional attention is an interesting inductive bias. The usefulness of inductive biases changes, however, across different computational scale regimes. At small scale, bidirectional attention gives an advantage. At massive scale, it stops mattering. A critical voice. Jan LeCun, chairman of the board of AMI Labs and Turing Award laureate in 2018, argues that the probability of error grows exponentially with each token. LeCun considers autoregressive models a dead end on the road to true intelligence, and promotes the JEPA architecture as an alternative. The decoder dominated the headlines, but in the background, millions of instances of models that GPT will never replace are quietly at work. The quiet renaissance of encoders. BERT has 68 million monthly downloads on Hugging Face. Is the second most downloaded model on the platform. Google Search has been using BERT since 2019. Nobody talks about this at conferences devoted to GPT-4 and Claude. The encoder is the quiet workhorse of production AI. The hard data speaks loudly. Filtering 15 trillion tokens in the FineWeb Edu project, $60,000 with a BERT-based model versus over $1 million with the cheapest Gemini Flash decoder, a difference of over 16 times. For any AI systems architect who knows only decoders, half the production pipeline is being designed blind. In December 2024, teams from Answer AI and Lighton presented modern BERT. Flash Attention 2 and 3, Rope, familiar from episode 8, 8,192 tokens of context, 16 times more than BERT. Training on 2 trillion tokens, 2 to 4 times faster than the BERTA. The key innovation is alternating attention. 2 local attention layers with 128 neighbors in a sliding window. Every third layer, full global attention. The effect? Elimination of the computational explosion when extending the window from 512 to 8,192 tokens. The ETIN study from 2025 confirms this systematically. Encoders with 400 million parameters outperform decoders with 1 billion parameters on classification and retrieval tasks. As the modern BERT authors wrote, wherever you see a decoder-only model in production, there's a good chance an encoder-only model is part of the system too. The reverse dependency doesn't hold. The cross-attention pattern, Q from one source, K and V from another, lives far beyond T5. Every RAG system is de facto an encoder-decoder architecture at the pipeline level. The retriever, typically an encoder-only embedding model, understands the query and documents. The generator, a decoder-only LLM, generates the response. Even multimodal models confirm this pattern. Lava connects the CLIP visual encoder with the Llama decoder. An architect who knows only decoders designs half the system blind. The mask shape determines capabilities. Time for synthesis. Free LLM architectures differ by one decision: the shape of the mask in the attention mechanism. No mask, encoder. Full L by L matrix. Every token sees every other. Understanding, classification, embeddings, retriever In RAG systems, BERT, modern BERT. Triangular mask with negative infinity, decoder. Lower triangular matrix. Token sees only the past. Generation, chatbots, code, reasoning. GPT, llama. Cross-attention with rectangular matrix. Encoder, decoder. Q from decoder, K and V from encoder. Sequence transformation. Translation, summarization, RAG system as a whole. T5, BERT. There is no best architecture. There are appropriate tools for appropriate tasks. The mask determines capabilities, and the practitioner must match the tool to the task. If this episode helped you understand why BERT and GPT are the same machine with a different mask, leave a comment with your experience. Subscribe so you don't miss the next episode on training stabilization, residuals, and norms. The mask determines capabilities. Thank you for your time.